Good morning everyone. Today we are going to start reinforced cement concrete. Well, what we are going to learn in reinforced cement concrete is different methods, then design of beams, slabs, columns, foundations, and pre-stressed concrete. Pre-stressed concrete. Okay. Well, first of all, what is concrete? Before learning all these methods of designing, first we should know what is concrete. Well, concrete is a proportionate mixture of cementing agent. It can be anything, cement or lime, cementing agent, then coarse aggregate, then fine aggregate, it is also known as sand, and water. Well, when I say proportionate mix, it means that these things are mixed in different proportions. Generally, we designate it as M10. For example, I am taking M10. This M is a mix and 10 is a cube strength after 28 days of curing, and it is in Newton per mm square. Okay, it is in Newton per mm square. The mix is 1:3:6. This proportion of M10 is 1:3:6. Similarly, different proportions is M15, which is 1:2:4. Then next is M20, which is it is 1.5. I'm just writing it again. 1:1.5:3. Well, M20 is the minimum grade of concrete recommended by IS code. It is a minimum grade recommended by IS code 456/2000. This is the code that we use for designing of reinforced concrete. Okay, so it is also a very important thing because it comes so many times in SSC, that what is the minimum grade of concrete. Well, so many students get confused between M15 and M20. Well, let me clear one thing. In the previous code it was mentioned M15, but in the recent code 456/2000, this is the minimum grade that we should take. Okay. Well, now going to the types of concrete. Okay. First is plain concrete, second is reinforced concrete. Well, the plain concrete is directly the mixture of cement, fine aggregate, coarse aggregate, and water that we discussed just now. That is a plain concrete. Then why do we need to go for the reinforced concrete? What is the extra in it? The extra thing that we used in the reinforced concrete is the reinforcement, which generally we used steel. That can be mild steel or HYSD bars. What these things are, we'll discuss about it later. Okay. Tor also we use. We'll discuss about this in details later, what it is. Okay. But still, this plain concrete that we are talking about, it is very good in compressive strength. Good strength in compression. Well, but when it comes to tension, it is very weak. The tensile strength of concrete is hardly 10 to 15% of compressive strength. So we can easily see that it is very weak in tension. So what do we do in our structure? Whenever tensile stresses are coming on our structure, what do we do? So that's why we go for a reinforced concrete. We used mild steel bars because steel is very good in tension. Steel is very good in tension. That is why we use steel bars in all the places wherever the tension is coming in the structure. Okay. Now, there is one more reason that we are using reinforced concrete is the failure of concrete. When we talk about the plain concrete, the failure of plain concrete is a brittle. I hope we all know that what is a brittle failure. Brittle failure is a sudden failure, like a glass. We all have seen what happens to a glass when it shatters. Like if you fall a glass, it directly shatters into pieces. So that is a kind of brittle failure. The same thing happens with concrete. There is a sudden failure. We also call it sudden failure. When it reaches its ultimate stresses, it fails suddenly. But we don't want our structure to fail suddenly whenever it reaches the ultimate load. That is the reason we use the reinforced concrete, because the reinforced concrete gives us significant warning before failure. It gives us significant warning. Okay? So, now let's go to the design methods. Before designing, we should know why we are designing. Why? What is the need of designing? Why don't we just use any sections that are already in use? Basically, the main objectives of designing are, first one is stability. Our structure should be stable. Stable means it should resist overturning or buckling. For example, if this is my frame, this is a column, this is a beam, it is a column, it is a beam, and any load is coming like this. So what will happen? It will go like this. And if this load is too much, then our structure can overturn. So we want our structure to be stable against this overturning. Now consider a column. If this is a column and we apply a load, then this column will buckle like this. But again, we want to resist this buckling. So these things comes under stability, to resist our structure under overturning and buckling. So it resists failure. Okay, this is the stability concept. Next is strength concept. People do get confused between stability and strength. Okay, but just listen. Strength means that your structure can easily carry the load that coming over it. Okay, that means it should carry safely the stresses induced in it. It means that, well, we'll take the example of the same column, that when your structure is under some load P and it buckles, then this buckling is under stability. Okay, but if this column just fails due to failure of material, if it fails due to failure of material, then it is known as strength. Okay, it should possess sufficient strength that it should not break due to less strength. Okay, so this is the strength and this is the stability. Stability means it should not bend or it should not slide, and strength means the material should not fail. Okay, well, now going to serviceability. What are the things which comes under serviceability? Our structure should not deflect or crack more than the permissible limit. Means it should resist deflection, cracks, vibrations under permissible limits. Well, now last and practically most important objective. Okay, practically most important is economy. When you are designing something on paper, then these three things comes the main criteria. But when you are on field, this also comes under main criteria. These four should be considered because we are going to need economy for this designing purpose. for execution purpose, sorry, not designing purpose, for execution purpose. Okay, so now we'll go about the, we'll read the different, sorry, we'll study the different methods. Well, first and very old method is WSM, or we can say working stress method. Next is ultimate load method, and third is LSM. First we'll talk about working stress method, WSM, or working stress method. Well, it came under the consideration in 1900. It is very old method. We don't use it nowadays. It is obsolete. Okay. It actually considered two things. It considered that material behaves in linear elastic manner. It considered the material behaves in linear elastic manner. And second thing, that safety is ensured by limiting permissible stresses. This method ensured the safety by limiting the permissible stresses. But how we can do that? No material is perfectly linear elastic. We have to make it linear elastic. For example, if we take the stress strain diagram of concrete, initially it is in linear elastic condition. Initially it is in linear elastic condition. After that, at 0.002 strain, it shows the maximum stress value, and after that the stress value decreases and the material fails nearly to 0.0035 strain. Okay, so we can see that initially it behaved as a linear elastic material. So instead of considering this full strength of material, we consider only the strength till here. That is the main reason that it gives the very large section. Due to this assumption, we get the first and main drawback of large sections. It gives large sections because this material can bear the load up to here. But what do we consider? That it can bear only load till here. That is why the factor of safety in working stress method is 3. In bending, 4 in compression. Okay, for concrete. These are for concrete. And for steel, we take 1.8. Okay, in both bending and compression. Okay, well, now going to the next thing that this method consider. Well, we all know that stress is directly proportional to strain by Hooke's law. Okay, Hooke's law says that stress is directly proportional to strain. So stress of steel is directly proportional to strain of steel. And since our concrete is a composite structure, okay, our concrete is a composite structure, so strain of concrete is equals to strain of steel. So actually this method considered a term which defines a relation between these two values. Okay, this method considered the term modular ratio, which is equals to stress in steel upon stress in concrete upon stresses in concrete. And we all know that stress by strain is equals to Young's modulus. So stress is equals to Young's modulus into strain. So we can directly say that ES into epsilon S upon EC into epsilon C is equals to M. But strain in concrete is equals to strain in steel. So you can cancel these two out. So modular ratio is ES by EC. So this method basically considered a term modular ratio which defines the relation between the stresses in steel and stresses in concrete, and based on this modular ratio the whole designing is based. Okay, but this gives the second drawback. Well, it gives a second drawback that we all know, we can see from here only, that this M is directly proportional to, it depends on the Young's modulus of concrete, and Young's modulus of concrete changes with time. Okay, it changes with time due to creep and shrinkage property. We all know that with age the concrete shrink and there are creep effects in concrete, so due to which the Young's modulus of concrete changes constantly with time. If we are talking about steel, steel is made in laboratories, sorry, not laboratories, in factories, so steel's Young's modulus will not change, but this Young's modulus which will change. That is the reason which gives us one more drawback, that this whole WSM is based on modular ratio, but modular ratio is not a constant thing because it depends on EC and EC changes with time. So this is one more drawback. Okay, well, one more important drawback of this method is that it does not take into safety considerations. Okay, sorry, not safety, serviceability. Okay, not safety, serviceability. It do not take serviceability conditions. Okay, well, in details we'll study about it later. Let's go to next method, ultimate load method. Well, in this the non-linear behavior of material is also considered. Therefore, it is designed for ultimate load. That is the reason it is designed for ultimate load. But still it does not give serviceability requirement. It do give safety requirement, but it do not give serviceability requirement. That is the reason we do not use it anymore. Okay, but still this method came into action because of this non-linear behavior that we discussed here, that in WSM we take only this much strength of a material, but in ultimate load method we took this much strength of a material. Okay, but still it do not give serviceability requirement. So next method, and the method that we use nowadays in every construction, is limit state method. Okay, it is a limit state method. Before going into deep about limit state methods, let's discuss very small things about it, that it takes safety, it takes serviceability, okay. So for the safety, in the limit state it has mentioned limit state of collapse. In the IS code it is mentioned as limit state of collapse, in which we have considered all kind of collapse conditions like bending, okay, then compression, then shear and torsion. Shear and torsion. And it has also given the serviceability requirements like deflection. It has given the deflection limits, that the deflection should not be more than this values. We'll talk about it later. Deflection limits, vibration limits. It is also given for corrosion and cracking. Okay. Now let's talk in detail about limit state method. First of all, we should talk basic things, what IS code has recommended for us to use. First thing is material strength. Material strength is basically the characteristic strength which means it is a strength below which not more than 5% of results are expected to fall. Okay, not more than 5% results. Okay, that means we take our, for example, we are taking concrete. Okay, we are taking concrete. Let's take M20 concrete. We will make M20 concrete cubes, and then we keep it for curing for 28 days, different number of cubes, and we test all the cubes in UTM machine. Okay, in UTM machine, universal testing machine. Okay, we test it in UTM machine and we'll get the results. Okay, so we take characteristic strength such that the result should not be more than 5%. Okay, now the design value, whatever value we got from the material strength, from that we find the design value. Design value is the characteristic strength. It is characteristic strength upon partial factor of safety. Upon partial factor of safety. Well, for concrete and steel we use different partial safety factors. 1.5 we use for concrete, and for steel we use 1.15. Why we are using different? Why not using 1.5 for both or 1.15 for both? Instead, why we are using 1.5 or 1.15 for steel? Well, the main reason is that the concrete is casted in sight. Okay, we test this concrete in a laboratory and find the characteristic strength, but actually when we are casting a concrete, we are casting it into a sight. So that is the reason the factor of safety for concrete is more than that of steel. Okay, now going to the imposed loads. What is imposed load and what is design load? Imposed load and design load. Imposed loads are loads which are coming over our structure. Okay, it is a characteristics load which has 95% probability of not being exceeded during life of structure. Means throughout the structure, throughout the life of structure, these loads value should not be more than 95%. Sorry, it should not. It has a probability of not being exceeded 95%. Okay. Well, now design loads. Design load is imposed load into factor of safety. Imposed load into factor of safety. Well, for different loads coming over a building, we have different factor of safety. For example, if we have load, dead load and live load only, then under a collapse condition, in that case we take the factor of safety as 1.5, and in case of serviceability conditions we take this value as 1. Well, if over our building dead load, live load and wind load is coming. Well, what is dead load and live load? First of all, dead load is a load which is coming due to our structure. That means column, beam, slabs. It all together gives us the dead load. Whereas live load is the load that we add up after the construction of this structure. That is living human being or the furniture that we keep over it, that we can change with time. That comes under live load. Okay. When dead load with wind load is available, then this value is 0.9 or 1.5 and this as 1.5. When we have all values, dead load, live load plus wind load, then this factor of safety becomes 1.2. When I am writing this 1.2, that means, for example, I have a dead load of 100 kilonewton, live load of 50 kilonewton and earthquake load of 20 kilonewton, then my design load will be 1.2 times into 100 plus 1.2 times into 50 plus 1.2 times into 20, means we have to multiply this factor into dead load, this factor into wind load, these factors into live load. Well, coming again to serviceability conditions, this value in serviceability conditions becomes 0.8 and 1. Well, now let's discuss the singly reinforced sections in bending. The first thing is bending. So in that also, first we discuss singly reinforced section. Okay. Well, let's take a beam. Okay, let's take a beam which is having two supports, simply supports, over which some load is coming, external load. Let's say it is W per meter. Okay, due to this load, the bending will be like this. Bending will be like this. That means the top fiber, if we enlarge this section, the top fiber will be in compression and the bottom fiber will be in tension. Okay. Well, now we'll take another type of beam, cantilever beam. What happens when it bends? It bends like this. So in this case, the top fiber is in tension and the bottom fiber is in compression. So when we need to provide the steel here, where do we provide? Of course, to the bottom side. So that is the reason in simply supported beams, the main steel is provided on the bottom side in simply supported case. But in cantilever case, it is a cantilever, it is simply supported. In simply supported, in cantilever case, we provide main reinforcement on top, because top is in tension and bottom is in compression. Okay, this here we provide bar to resist tension. Well, now let's talk about stress strain diagram of concrete in compression. See, here you can easily see that the top fiber is in compression. So what is resisting this compression? Concrete. And bottom fiber is in tension. And what is resisting this tension? Steel. So we need to study the stress strain diagram of concrete in compression and stress strain diagram of steel in tension. Okay. So first let's study stress strain diagram of concrete in compression. We all know that our concrete is very good in compression, and as I told you before also, that initially it behaves as linear elastic, then it behaves as parabolic, and then after attaining the peak value it drops. The value at which generally it gives the peak value is 0.002, and this value is FCK. Okay, this is stress, this is strain, and we have seen that generally at 0.0035 our concrete fails. But since this parabola is bit this parabola is bit difficult to analyze, so what we do for our analysis purpose, we take it as a straight line. Instead of taking it as curve, we take it as straight line. So the strength of this concrete is FCK. This is a strength of cube. Okay, this is the strength of cube after 28 days of curing. Okay, well, but in actual practice, do we use cube? No. In actual practice, we use generally slabs, beams, column which are not cube. in fact which are cuboid. So we have to apply a factor of safety. And what is the factor of safety for concrete? 1.5. So it becomes 0.67 times of FCK. This is the strength in structure. Strength of concrete in structure. Well, now for design purpose we do need to provide one more factor of safety. Let me write it here. 0.67 FCK upon 1.5. It becomes 0.446 FCK, and it is the design curve, or we can say it is a design strength. We use this particular curve for our design practices. This is a parabolic portion, this is a straight line portion from 0.002 to 0.0035, and this we have assumed as a straight line, okay, for our analysis purpose. Now going to the next part, stress strain diagram of mild steel. Stress strain diagram of mild steel in tension. I've already told why we are going for tension, because we use mild steel in tension side only, so that's why we need to study this diagram. So when a mild steel bar is stressed in UTM, it is seen that initially it follows a Hooke's law, then it reaches an upper yield point, then lower yield point, and there is a yield plateau. Okay, that means the mild steel bars do not have a definite yield point like a concrete. See, this concrete had a definite yield point. But this mild steel bar do not have a definite yield point. So all the materials which do not have a yield point, we consider yield point at a proof strain of 0.1 to 0.2. Okay, that means we take an offset from this at 0.1 to 0.2. Our IS recommends that we should take 0.2% strain, okay, 0.2% strain, and due to this yield plateau, this diagrams becomes bit more complex. So we generally normalize this curve, and what we do that till this portion we take the same, and after that we take a straight line just for normalizing. Okay, this is a normalizing of a curve. Okay, well, again it do not have a yield point, so what do? We have to take a 0.2% of strain. Okay, that means 0.2 means 0.002. From 0.002 we have to take an offset which should be parallel to this line. Okay, well, before going through this, let me tell you, if the strength of steel is Fy, then we apply a factor of safety of 1.15, and it becomes 0.87 times of Fy. Okay, so now we need to find this strain value. How do we find it? We have already told that we should provide a proof stress of 0.002, sorry, proof strain of 0.002. So this value is 0.002. Now we have to find this value. Now from here to here it follows a Hooke's law. From here to here it follows a Hooke's law, and Hooke's law says that stress is directly proportional to strain. That means stress by strain is equals to Young's modulus of that material. So we can directly say that strain is equals to stresses by Young's modulus. If we see this triangle, this values of stresses is 0.87 Fy by Es. So that is the value of strain at failure. Okay, so the strain value of steel is equals to 0.87 Fy by Young's modulus plus 0.002. In actual practice, it should always be greater than this value. Okay. Well, what is the Young's modulus of steel? Young's modulus of steel is taken as 2 into 10 to the power 5 Newton per mm square. Okay, even in exams they may not give you the value of Young's modulus of steel, so you should know the value of Young's modulus of steel. So now going to the assumptions of limit state method. The very first assumption is the section before bending remains section after bending. That is, plane section normal to axis before bending remains plane after bending. It means that if it is a beam, and this is my section that I am talking about, any section I can take, okay, then after bending also this section remains straight, okay, it do not bend like that, it still remains same. This is our assumption, our very first assumption, that plane section normal to axis before bending remains plane after bending. Why do we consider this? The main reason for considering this assumption is because when we consider that it do not bend, then there is a linear variation in strain. Okay, for linear variation of strain we assume this particular thing. Okay, so plane section before bending remains plane after bending. This is the very first assumption. Bending remains plane after bending. Well, next is that we have already seen in the last slides, that maximum strain in concrete is 0.0035. This is also our assumption. Next, maximum strain in steel, it should never be less than 0.87 Fy by Es plus 0.002 that we just talked about in last slide here. Okay, it should always be greater than this value. Well, last and one more, tensile strength of concrete is ignored. Okay, that we assume that concrete do not possess any tensile strength, all the tensile forces are taken by steel. Well, now going to the main and very important things is stress block parameters of concrete. Since we have considered a singly reinforced section, that means let me consider a beam whose width is B and effective depth is D. When I say effective depth, it means total depth minus cover. Total depth minus cover. That means if I am providing mild steel bar here and this is my cover, then this will be my effective depth and this will be my total depth. But in designing purpose, we only consider effective depth. Now, we talked about it before that if in simply supported beam any load is coming, then it bends like this, due to which the top fiber is in compression and bottom fiber is in tension. So, top fiber will be in compression, there will be compressive forces, and bottom fiber there will be tensile forces. So, of course, by common sense we can say that in between these so many fibers, there will be one fiber which do not have either compressive forces or tensile forces. Okay, that particular fiber is known as neutral axis. That particular fiber is known as neutral axis. Neutral axis is basically a fiber which do not have any compressive stress and any tensile stress. So, according to first assumption, as we have considered a linear variation in strain, if I see the strain diagram, what is the strain value that we have considered for concrete? Maximum strain value 0.0035, and the value of that for steel 0.87 Fy by ES plus 0.002. Okay, next thing is ये हो गया हमारा strain diagram. Next we'll go to the stress diagram. Well, we all will see that why this diagram is like this. Why we have not taken any diagram like this? Why particularly this rectangular then followed by parabola? Well, this particular diagram has come from the stress strain diagram of steel. Not steel, sorry, concrete. See, in this slide we talked about stress strain diagram of concrete. From this diagram we have taken this curve as our design curve, and we have put this design curve here. See, what we saw there, that till 0.002 it is a parabola. That means from it is a 0 place, from 0.0 till 0.002 it is parabola, and after that till 0.003 it is straight line. Okay, so this is 0.002. Now this is 0.446 times of FCK. Well, there are so many things in this diagram that we don't know, like these value, this value, this whole value, this value, this compressive force value. So we are going to find all these values now. Okay, first we'll find the values of these two. That is, let us consider that this distance is A and this distance is B. How do we find this? Well, we'll go to the strain diagram. Okay, we'll go to the strain diagram and we consider these triangle OAB and OPQ. We can easily see that these two triangles are similar triangles. Okay, so triangle ABO is similar to triangle PQO. So we can say by the similar triangle properties 0.002 divided by B is equals to 0.0035 divided by this whole value. Let us name this depth of neutral axis as XU. XU is depth of neutral axis. Okay, we'll also find it later. First let's find these values. Okay, so if you solve this value, you get the value of B as 4/7 times of XU. This B becomes 4/7 times of XU. Well, this is very important from examination point of view. You should know this diagram as it is, because so many times they ask, in SSC they have asked so many times that what is the depth of rectangular portion of stress diagram, or what is the depth of parabolic portion of stress diagram. So you should know these values. Okay, well, so now we know this value, this value. Now what do we need to find next is total compressive force acting and total tensile force acting. Okay, we'll go to the next diagram, next page, sorry. I'll draw that diagram here again so that we can talk about it. Okay, well, this value was 0.45 or 0.446 FCK. Okay, this is 3/7 times of XU. This is 4/7 times of XU. Well, the total compressive force is the area of this stress diagram. Okay, so if we take the area of this block plus this block, we get the stress, sorry, not stress, we get the total compressive force. So total compressive force is given by area of stress diagram. Okay, why we are taking the area of this whole stress diagram? Because the concrete present here will of course bear this whole compressive stress coming over it. That is the reason that on the bottom side we have only taken a straight line as a tensile force, because here the tensile forces will only be resisted by the mild steel bar, which is present only in this section. That is the reason it is a straight line here, and it is a combination of rectangle and parabola here. Okay, so let's take the area of this diagram. What is the area of rectangle? Length into breadth. So we can easily say 3/7 times of XU into 0.446 FCK. Of course, it is acting of per meter width, so we have to consider width. Now, taking the parabola, what is the area of parabola? 2/3 times of length into breadth. That is 2/3 into 4/7 of XU plus 0.446 times of FCK into, not plus, multiplication, FCK into B. So, if we solve these values, what we get is 0.36 FCK XU into B. This is the compressive stress value that we get from this thing. Now, talking about the tensile stress or the tensile forces coming, we know that the tensile forces are, what bear tensile forces is mild steel. This mild steel bars bear the tensile forces. Okay, so, and we know that force is equals to stresses into area. Stresses into area. So what is the stresses of steel? 0.87 Fy. Considering the factor of safety, it is 0.87 Fy, and area of steel is AST. So the tensile force, total tensile force is 0.87 Fy into AST. Okay. Now, next thing is, compressive force is acting at what distance from here? We should know, of course, we should know that at what distance this compressive force is acting. So, we have a rectangle, we have a parabola, we just need to find the CG of this force. How do we find? Now, next thing we need to find is position of compressive force, or we can say position of C. Okay. So, how to find CG? Let me take this as a datum. Okay. So, I will take the area of this rectangle and find the CG from this particular datum. So, what was the area? Area is this value. Okay. This is 3/7 times of XU into 0.446 FCK into B, and CG of a rectangle is B/2 cross D/2. So, we can easily say that it is 1/2 into 3/7 times of XU. Okay. So, this is first term. Then next term is area of this value plus, area of this value into distance of this from this, like area of this value, then distance of this compressive force from this datum. So, we have calculated area here, we will just write this value here, 2/3 times into 4/7 XU into 0.446 FCK into B. Okay, this is the compressive force, and it is acting at a distance of, for a parabola, the CG is at 1/3 from here and 2/3 from here. Okay, so from here it will be 1/3. So 1/3 into 4/7 times of XU plus 3/7 times of XU. This is the distance. What I have added is 1/3 times of this value, that means this plus this. Okay, this makes the total perpendicular distance of this force from this datum. So, when we solve this value, it becomes 0.42 times of, sorry, we have to divide this whole value by total area. That means this value, this whole value we have to divide from this value, that is 0.36 FCK XU into B. So when we solve this value, we get the position as 0.42 times of XU. So let's mark it here. This is 0.42 times of XU. Okay, you should also remember this value. Okay, this is 0.446, this is 3 by 7, this is 4 by 7, this is 0.42 times of XU. Let us also mark it here, 0.42 times of XU. Now, coming to what is this XU? Okay, now let's talk about XU. XU is depth of neutral axis. That we already talked about, that what is neutral axis. Neutral axis is basically an axis on which there is no compressive force or tensile force. It is free from any kind of forces. Okay, so that is a reason in a that is a reason that in a stress diagram the stress is coming over it is 0, and also in strain diagram also the strain coming over it is 0. Okay, because it is a neutral axis. Now coming to the depth of neutral axis, how do you find the depth of neutral axis? Well, let's talk about the limiting depth of neutral axis. In every material or every structure there is one limiting value. Okay, that limiting means maximum value. There will always be a maximum value of this neutral axis depth. To find that neutral axis depth value, we need to again consider this strain diagram and the similar triangle values. So let us draw that strain diagram here. This is 0.0035, this is 0.002 plus 0.87 Fy by ES. Now take this as O, this is A, B, this as PQ. Now OAB, triangle OAB is similar to OQP, This is a symbol of similar, okay, when we are designating similar triangles. Okay, so since this is a similar triangles and this depth is XU, this depth is D, so what we can take 0.0035 upon XU equals to 0.002 plus 0.87 Fy by ES upon D minus XU. Okay, here we take D minus XU. Okay, so if we reverse it, what it will become? 0035 equals to D minus XU upon 0.002 plus 0.87 Fy by ES. Now we'll take this thing here and we'll bring this XU here. So what it will be like? 0.002 plus 0.87 Fy by ES upon 0.0035 equals to D minus XU upon XU. So if you solve this, it will be D upon XU minus 1. Now if you take this minus 1 to that side, what it will become? Plus 1 here. Now if we are solving this value, this 0.0035 will go here and add up to this value. So D by XU becomes 0.0035, sorry, not 35, 55 plus 0.87 Fy by ES divided by 0.0035. So the value of XU becomes 0.0035 upon 0.0055 plus 0.87 Fy by ES. So we can easily say that the limiting value of neutral axis only depends on material steel. It only depends on steel, not concrete. So this is also one of the most important questions in SSC JE exams. Then that axial limiting depends on which of the following. So you should always remember that axial limiting always depends only of the properties of steel. So for different type of steel, these values are different. So axial limiting by D, if you put Fe 250 in this value, ES is equals to, of course, I have already told you that ES is 2 into 10 to the power 5 Newton per mm square. Okay. So if you put these two values for Fe 250, this value of axial limiting by D is 0.53. Okay. Then for Fe 415, this value is 0.48, and Fe 500, this value is 0.46. Okay. For simplification, you should always remember these values in exams because they do ask the direct values. Okay. And again, if you do not remember these values, then to find axial limiting, you again have to waste the time in exams. So it's better that you remember these values according to the exams. Okay. Now let's go to C and T. We have found that this is the compressive force. Let me go. This is the compressive force and this is a tensile force acting on our structure. So what happens when the structure is in equilibrium? So in equilibrium conditions, of course we know that compressive forces will be equal to tensile forces, or we can say that 0.36 FCK XU into B is equals to 0.87 Fy into AST. Okay. So from here we can easily say that XU is equals to 0.87 Fy AST upon 0.36 FCK into B. From here we can find the value of XU, and this was the value of axial limiting. Don't forget, this is the maximum value. Okay. Maximum depth of neutral axis, and this is the actual depth of neutral axis, which is according to our loading conditions. See, you can easily see that this is according to our width, our depth, and according to area of steel. So it is according to neutral axis, sorry, according to So now you can say, since we have kept this XU limiting in the terms of XU by D, so we can also keep this XU in the terms of XU by D. So it makes this value as 0.87 Fy AST upon 0.36 FCK B into D. Now by comparing these values, XU limiting by D and XU by D, we can classify our structures, not structures, our sections. Okay. Based on these values, we can classify our structure. If XU limiting value, that means the maximum neutral axis depth value, is greater than the actual value. That means if this is my structure, this is my XU limiting, then my actual neutral axis will be above it. So what happens? In those conditions, our steel, the steel here, reaches the maximum value first. That means TU reaches maximum value first, or we can say that TU reaches maximum value before CU. Okay. We can also name it as CU and TU instead of C and T. Okay. So if T reaches the maximum value before it, it becomes under reinforced condition, or we can also say our structure is under reinforced section. And in this case, if we have to find moment, what is moment? Moment is of course force into perpendicular distance. In this case, T reaches the maximum value first. That means T is greater than C. So of course we take the value of TU for the calculation of moment of resistance. So what we do is TU into perpendicular distance. Now what is the perpendicular distance between these two forces? See, this is C, this is T. What is the perpendicular distance between these two forces? this, we can also call it as lever arm. Okay, this is equals to d minus 0.42 times of XU. See, this whole is d, from here to here is d, and from here to here is 0.42 XU. But we need to find the value from here to here, so d minus 0.42 times of XU. So, moment of resistance will become Tu into perpendicular distance minus, that means d minus 0.42 times of XU. That means it will be 0.87 F5 AST into d minus 0.42 times of XU. Well, this question was asked in this year's Jal Nigam question paper of UPPSC. They asked that if it is under reinforced section, then what will be the moment of resistance value? So it should be according to tensile forces. Okay. Now, next, what will happen if these two values are equal? XU by d is equals to XU limiting by d. Then our section will be balanced. Balanced section. So in these values, in this one, actual neutral axis depth and limiting value, neutral axis, will be at the same position. That means we can find the moment from any value, like we can find by T into lever arm, or we can also find by C into lever arm, because both forces values are same. Okay. So we can say that 0.87 Fy AST into d minus 0.42 times of XU, or we can also write it as 0.36 FCK XU into B into d minus 0.42 times of XU. Now what happens when XU by d is greater than XU limiting? Because we have said that neutral axis cannot go beyond the limiting value. If this is the limiting value, then neutral axis should never be, can never go beyond this value. So what will we do if this condition arises? We have two methods. First one, we can over reinforce the beam. Okay, first thing that we can do is that we can over reinforce the beam, or second thing we do, redesign our beam. Okay, that means we can reduce the sections, sorry, not reduce, we can increase the sections and then again find XU, or we can also keep the reinforcement in compression side, that is the over reinforced case. So in exam they ask that if XU by d is greater than XU limiting by d, then from the following which one is true, that it is over reinforced section, under reinforced section, or balanced section, or none of the above. So that you can also say that it is over reinforced section, or you can also say if there is an option that you have to redesign a beam. Okay, both the things are correct. Sometimes they may give 2-3 choices, like they give statement 1, statement 2, statement 3. Okay, out of which you have to choose that which statement is true. They can give these two statements, okay, together. So you should know that when this condition arises, you can also design it as over reinforced beam, or you have to redesign your beam and increase the section. Okay, when I say increase the section, that means you have to increase B and D. Okay, and in this case the moment that will be calculated, well, let me go to the new page. The moment that will be calculated will be the limiting moment. Okay, and its value will of course be with respect to C, which is FCK XU limiting into D minus 0.42 times of XU limiting. Okay, now it's only till here in the singly reinforced section. After that we will go for the designing in the next class. Thank you.